Hi, and welcome to the second video on basic acoustics for recording. In these follow-up videos to the first one, I want to delve deeper into some of the concepts that I mentioned in the first video, but said that I would leave for another one to explain. In this video, I want to talk about something called phase and a phenomenon called phase cancellation. This is quite a tricky concept to understand sometimes because essentially the best way to understand it is mathematically, but I like to take it out of the mathematical world and try and apply it to something that we can all understand more easily. The thing about phase is that although it's quite complex, it's a phenomenon, and phase cancellation is a phenomenon which crops up again and again in audio production. Although I'm talking about it in terms of acoustics and recording here, phase and phase cancellation are important at every stage of audio production. It doesn't matter whether we're talking about audio that you've recorded and is stored in your computer, or sound that's being played out of loudspeakers, or indeed sound that's being recorded as it hits a microphone. Phase and phase cancellation are really important at every stage of that. So I want to take this whole video to explain what phase is, why phase and phase cancellation are important things to understand, and when it's likely to happen, particularly in a recording scenario in this video. So first of all, to demonstrate phase cancellation, I'm actually just going to move the microphone next to a wall and cause some natural phase cancellation on my own voice so that you can hear it. I've now got the microphone right next to a wall, and I am right next to a wall as well. And you'll notice that my voice will have changed slightly in tone, almost a textural change. It may sound more or less bassy than it did before when I was sat in the middle of the room recording. This is occurring thanks to a phenomenon called phase cancellation, which is happening inside the sound that's being reflected by the wall and the sound that's coming directly out of my mouth. And it's something to do with the way they interact with each other when they meet. So you've heard that phase cancellation essentially changes a sound. This isn't necessarily a good thing because when we're producing audio, we'd like to record the sound as naturally and as realistically as possible, and then if we want to make changes to it, we will, but we don't want any baked-in changes or any spooky weirdness thanks to phase cancellation. To know what phase cancellation is, first we need to know what phase is. So I want to return to that old original view of the waveform. This time, we're looking at this 2D waveform in terms of time. So we can imagine that these waves are actually pressure waves in the air, high and low pressure, proceeding forwards in time. And this is a sound wave, and again, it's something we're quite familiar with. If I was introducing a second exact copy of this sound to the image, which I just have done, then we can start to use that to understand what phase actually is. See, phase is just a term that's basically used to describe the way two waves, which may be identical, line up with each other in time. So when I say identical, what I actually mean is they're identical in shape. They have the same height or intensity, which for us is related to loudness. And they have the same wavelength, which means they have the same frequency, or they have the same amount of waves over the same amount of time as each other. The second wave I just introduced is difficult to see at the moment because it's what we would call perfectly in phase with the original. That means they line up exactly with each other. But if I move it out of phase, you'll begin to be able to see it. And as it slides slowly out of phase, we begin to see it. So we could say that these two waves are now out of phase, meaning that they don't perfectly line up with each other anymore. When they're in phase, it just means they line up perfectly. If I were to move the second wave even further in time, eventually it would go all the way until it was back in phase with the original, lining up with it nicely in time. We call that a 360-degree phase shift. The thing that we need to remember is that when the waves line up perfectly, they're in phase. And when they're exactly opposite to each other, in other words, when the trough or the dip in one wave lines up perfectly with the peak of another wave, they are exactly out of phase. When this happens, a phenomenon called phase cancellation occurs. If you imagine that these waves are actually pressure moving through the air, which again is just what sound is, then when the high pressure from one wave meets the identical low pressure pocket from another wave, they actually fill each other in, meaning the waves cancel each other out and the sound disappears. We can understand immediately why this would be bad for recording. You can't record a sound that has been destroyed by phase cancellation. Now, we might assume that phase cancellation is extremely rare, because how often do you really notice sound just vanishing for no apparent reason? Probably never. The reason for that is because actually, the view of sound that we're looking at here, this nice friendly wave, is imperfect. It's oversimplified. What we're looking at here would represent only one frequency of sound. In reality, natural sounds are composed of many, many frequencies. Let me show you what real sound looks like. It looks like this. My voice, your voice, a drum, a bird singing, a rainstorm on a cloudy day. They're all composed of multiple frequencies of sound happening at the same time. That means multiple overlapping waves of different frequencies, of different heights or intensities, therefore loudnesses, all occurring at the same time. It's almost chaos. And this is why phase cancellation really matters. Our ears can hear from 20 Hz to 20,000 Hz. That means they can hear any frequency of sound from essentially 20 waves passing us by per second, all the way up to 20,000 waves passing us by per second. That is a lot of waves. There are bound sometimes to be some waves that cancel each other out in the way I just described. When that happens naturally, that's fine. We consider it part of the natural sound. But when it happens unnaturally as a result of something we've done, we're actually damaging the sound and we're no longer capturing it in its full glory. So when does that damage occur? Well, as you've probably guessed from the fact that I moved the microphone next to a wall to record the little example at the beginning of this video, one of the places it can happen is when sound gets reflected from a solid object. Let me show you how. Let's go back to a simplified view of sound where we will just look at one frequency, because it's a lot easier to draw and it's a lot easier to understand. So we're just going to take one frequency from a natural sound, isolate it and look at that. It proceeds through the air as a wave, a series of peaks and troughs in pressure. And we're all quite happy and familiar with that. But what happens when it hits something? A wall, for example. Let me draw in a wall here. We know that sound reflects. It will travel back along the path it came in from, and we would hear it as an echo, or to give it its proper name, reverberation. So let me draw in the reflected wave. It was increasing in pressure as it hit the wall, so as it reflects back it's going to continue to increase in pressure. And it will just carry on following its familiar wave pattern as it did before. And oh dear, you can already see, perhaps, that we have a problem. Aside from the fact that I'm just really bad at drawing waves, which sucks for somebody in my position. What we can see here is that the reflection is out of phase with the original sound, meaning that they're going to interfere with each other. They're going to destroy each other. That frequency of sound will be gone, essentially. So if my microphone was near the wall, some of those reflections coming back would be more than loud enough to destroy the direct sound travelling into the microphone and make changes to it. And that's what you could hear in those examples I recorded for you at the beginning of this video. That's why even in a room where you can't necessarily hear the sound reflections or hear the echo, it's important to try and position your sound source and your microphone as far away from reflective surfaces as you can get them. It will minimize the amount of phase cancellation you encounter. Why? Because as we know, sound loses pressure, loses intensity, and therefore loses loudness the further it has to travel. So if that reflected wave that's out of phase travelling back to our microphone has become very small because it's had to travel a long way, it will cause far less damage to our direct wave, which will still be nice and strong and loud because it's coming straight out of our voice, straight into the microphone. So this is why even if you can't hear sound reflections, you should still remember that they're there and they can still cause damage. We will be talking a bit about phase throughout the module. I'll try and keep it as low maths as possible, because really all we need to understand is what it means and why we want to be aware of it. But for now, I hope we've achieved that. Thank you for listening.